Uh, Good afternoon to all, to the participants as well as the dignitaries. This program has the title Understanding Weed Loads on Structures. The topic will be again subdivided into two parts. One is wind and its applications in the design of structures, which will be delivered by Dr. Prem Krishna. And the second topic is features of IS 875 Part 3, 2015 and the way forward, which will be delivered by Dr. Abhay Gupta. So a little bit of Dr. Prem Krishna, so he needs no introduction, but still to continue with the formalities, Dr. Prem Krishna obtained his bachelor's degree from the University of Roorkee in civil engineering in the year 1959 and master's in 1961. He obtained a doctorate from Imperial College London in 1964. He then joined as the Faculty of Civil Engineering at the University of Roorkee in 1965 and then retired in 1998. Otherwise also, his teaching assignments were at the University of Illinois, Urbana, USA, and Imperial College of London, UK, from 1968 to 1970. Dr. Prem Krishna started his R&D in the field of wind engineering in 1978, basically to tackle the industrial wind engineering problems in the country. He took the initiative to organize the first Asia Pacific Symposium on wind engineering in the University of Roorkee in 1985. With the help of few other colleagues, he set up the Indian Society of Wind Engineering in 1993. He was the first president and stayed there for 7 years. The ISWE organized successfully the 9th International Conference on Wind Engineering in Delhi in the year 1995. Okay, so just to repeat, important professional memberships, Fellow of and Vice President, Indian National Academy of Engineering, 2008 to 2013, Founder President, Indian Society of Wind Engineering, 1993 to 2000, President, International Association for Wind Engineering, IAWE, 1991 to 1995, Chairman, Research Council, CBRI Roorkee, 2010 to 2017. Awards and honors, IAWE Presidential Award for Career-Long Contributions to Wind Engineering, given for the first time by IAWE in 2021. Distinguished Alumnus Award 2012, IIT Roorkee. Lifetime Achievement Award by the ISWE, celebrating 20 years of its establishment. So this is in brief the CV of Dr. Professor Prem Krishna. But before we hand over the proceedings to Dr. Prem Krishna, I would request DG Insdag, Mr. P.K. Mishra, to deliver his speech. So over to Mr. P.K. Mishra.
Thank you, Mr. Ghosh. Again, it's my privilege that I am sharing this virtual platform with great eminent professionals like Professor Prem Krishna and Professor Gupta. And I'll just take 2-3 minutes to talk about the institute, and I'll do it through a small PPT of 2 to 3 minutes. I'll just take, because there are many part of the many members who are in this audience who may not be knowing about the Insdag. So it will be helping us to share what we are doing here, what is our objective, and how we can take things forward. So that is what I would like to state in this PPT. I'll just take 2 to 3 minutes. This institute is in service from 1999. In fact, this was set up in 1996, but the operation started in 1999. We have already completed 25 years, and our objective is how to augment usage of steel, mainly in construction sector. And this is a not-for-profit and a member-based society. This is promoted by Government of India Ministry of Steel, and founder members include SAIL, JSW, Tata Steel, ArcelorMittal, and RINL. Other than the founder members, we are presently having about 95 numbers of institutional members and 620 of general members. And Executive Council, which is the top management body of this institute, is headed by Mrs. Swam Mandal right now. She is the chairperson of SAIL, and other distinguished members of this Executive Council are Mr. T.V. Narendran, head of Tata Steel, Mr. Sajan Jindal, head of Jindal Steel, Mr. Dilip Omen of ArcelorMittal, and Mr. Atul Bhatt, CMD of RINL. Insdag has a team of expert civil and structural engineers who have contributed in a big way in the field field of steel intensive designs and other activities like codings. Insdag was directly involved in making and bringing out, the standards such as IS 800, IS 801, IS 11384, and presently also Insdag is member of various committees of BIS and IRC. Till today, Insdag has completed about 70 major projects during last 25 years, and more than 100 technical publications have been made by Insdag. Many steel-based designs, particularly for low-cost houses, have been made by Insdag. And right now, we are also engaged with, Ministry of Steel for PMAY program, where a committee has been constituted, and Professor Murthy of IIT Madras, he is the chairperson, and we are involved in propagating this low-cost steel design houses. Some of the major publications are stated here: Guidebook on Welding and Fabrication of Structural Steel, Guidebook on Use of Stainless Steel Construction, and Building Design with Steel Hollow Section. And quite a few projects are also we are right now undertaking. And one of them is the design of steel bridges for MORTH, the Ministry of Road Transport. And one set of design, that 30-meter span bridge with 13.5-meter width, we have already, it has been already made. Insdag is the convener of this committee, and this set of design has been already, drawing has been already approved and sent to MORTH for implementation. We are also working on another 5 sets of design for 30-meter span bridge. We are also right now undertaking, once again, we are trying to undertake, earlier we had undertaken the study of life cycle cost. When there are some queries from the Finance Ministry, we are also trying to undertake once again life cycle cost analysis, and also we are doing a study of steel composite box girder. Insdag is capable of undertaking consultancy, third-party inspection, and providing one-stop solution for steel structure. I'll just take 1 minute. Many of the clients, many of the steel users, they know the benefits of steel, but perhaps they don't know who can provide the one single window solution for design, providing the steel, executing the project, looking after the inspection or the third-party quality inspection. So Insdag also is trying to, as a novel initiative, we have started taking up this kind of project also. And now we are engaged with some of the clients like Steel Authority to provide one-stop solution for steel-based structures. And through this platform also, I'll request others who are listening to me, in case there is any such requirement for any service of Insdag, we'll be too happy to demonstrate our expertise, because I personally believe theory part, making paper, making study is one aspect that is good, but how to execute them in real life, how to demonstrate the utility of steel, that's also another thing. So both the ideas we are trying to take forward. And we want, I was just mentioning to Prem Krishna sir and Gupta sir, we also want to make Insdag a reference point for training on structural engineering with regard to steel structure. That's our purpose, and we are going to have our new website. You can see right now we are having our website, but it is still under construction. There we'll have a training calendar. Particularly, I'll be taking the help of expert like Professor Prem Krishna sir, and we'll have a training calendar. So people all over the country, they can see that what kind of training modules are available in Insdag and how they can be benefited. We are a not-for-profit organization. We are not going to charge too much of money, but we like that our whatever expertise available in this institute, that should be put into use for the benefit of steel users and steel fraternity. Thank you, Professor. Thank you.
Thank you, sir. So for the participants, there is one announcement. The chat box is open. So whoever wishes to ask any question should put it in the chat box so that the lecture is uninterrupted. And at the end of the program, we'll be sending you a feedback form for your feedbacks for obvious reasons. Now over to Dr. Prem Krishna for his lecture, Wind and its implication in the design of structures. Sir, over to you, Doc.
Well, good afternoon, Mr. Mishra, Mr. Ghosh, my colleague, Dr. Abhay Gupta, and all the participants on call in this program. I would like to compliment Insdag for starting this series of lectures. And one hopes that through these we shall be able to disseminate parts of latest know-how that we have and share with the participants the experiences that we have. It's good to hear Mr. Mishra about his plans, and I really wish Insdag well in these ventures. I have personally been involved with Insdag for almost 2 decades now, and one hopes that Insdag will continue to take central position in as far as steel structures are concerned. Coming to the subject of our discourse today, as has been explained, it is to do with wind and its implications in the design of structures, and it's being shared between me and Dr. Abhay Gupta. When you have a former student sharing a lecture program with you, you have the benefit of doing what you like and leave the difficult part to him. So my part is comparatively simple. I want to describe what wind is and how it, what are the implications to us in the design of structures. And then the more expert part comes from Dr. Gupta on tall buildings. Today we are focusing more on buildings rather than other kinds of structures like bridges and chimneys, which have additional dimensions. So my part of the presentation is, as I said, comparatively simple, and I see stalwarts in the amongst the participants like Dr. Harshvardhan, and I know they know all about what I'm going to say, so kindly bear with me. I now share my presentation with you. As the title of the presentation says, wind and its implications for structural design. And let me go to the As we indeed know, wind is a natural hazard. The location or frequency for windstorms are not specific. They are random. And we have no control over this natural hazard. So obviously, our concern as engineers is to minimize loss and destruction. Loss of life, loss of property, loss to production, loss of agricultural produce, and so on and so forth, and destruction to structures and installations. The engineer's mandate is the safety of structures and installations. Now, first, a few words about wind itself. Wind flow generation is on account of atmospheric pressure differentials. The temperature differentials play a big part, and to extent moisture. And the wind velocity generated is essentially dynamic, randomly varying in both time and space, as well as direction. So we are dealing with a natural phenomena which does give us many challenges because it is randomly varying, it's dynamic, and so on and so forth. This slide here explains, or rather typifies, the kind of wind velocities that one experiences. This top figure here this figure here, if one were to measure velocity at a point in space, well, this is the kind of trace that one will get. As you can see that there is a lot of fluctuation in the value of the velocity. And in fact, for convenience, one can break this down into a mean value and the fluctuating values. The fluctuating values are what represent the turbulence in the wind or the gustiness in the wind. And the mean value is as I've shown here. So it is a combination of a mean value and a fluctuating value, which, as I said, is a measure of turbulence or gustiness. Now, likewise, if one were to see the variation of wind velocity with height above the ground, then this is the kind of variation you will find in the wind velocity. The mean wind velocity will vary like this, and it is right overridden with these fluctuations or the gustiness. The gustiness, as you will notice, decreases as you move from ground upwards and does reduce a bit substantially as you go up above the ground. So the maximum turbulence that you will experience is nearer the ground, as is expected in a boundary layer flow. Now, whatever be the nature of the storms that occur due to wind, this is basic. It is dynamic, it is randomly varying. And this variation here is the one that you experience in boundary layer winds, monsoonic winds, gales, dust storms, and so on and so forth. There are other kinds of storms, which I will very briefly indicate to you. The structure of variation can be different. Now also, if you go across perpendicular to the board into space, then also you find that there is a correlation between values of wind velocity, but they are not fully correlated. So therefore, again, there is a variation as you will experience if you go across into space. So it is randomly varying, not only with height, with time, into space also there is variation. So now going a little forward with this. Yes, I mentioned that wind storms, this wind flow that occurs manifests itself into various forms of storms. Monsoonic winds, we are familiar with. localized storms, can be dust storms or different kinds of gales. And these together occur all over the country. More or less is the only difference, but everybody in this country, all over the country, these are experienced. And I might mention that this kind of winds forms the basis of most of the wind loading codes. IS 875, no exception. That's the boundary layer wind or the synoptic wind is what you make as a model for laying down stipulations in the codes of practice for loading. Then the other kind of storms that I've listed here, cyclones, we call them cyclones. The American continent hurricanes, the Japanese call it typhoons, but they are the same thing. These essentially emanate from the sea and move inwards towards the land. The special part about these is that they are characterized by circulatory motion, and that circulatory motion is constituted with very high wind speeds. 55, 60 meters per second, even higher, is not uncommon. Also, a cyclone brings with it storm surges, maybe 5 meters high, 6 meters high, or even higher. It also brings with it heavy rains. So therefore, a cyclone will give you high wind velocities and it may cause flooding on the coasts when a cyclone occurs. Then we have these three listed here: tornadoes, thunderstorms, downbursts. I often think we might not call these windstorms, but nevertheless, these are often listed as. And tornadoes. Now, all these three are, at least in our country, what I should say, not very common occurrence. Tornadoes do not occur very commonly in our country. Thunderstorms, downbursts, of course, occur. And but these are localized activity. The difference between these three on the top here and these is that these are localized, narrow band activity, if I may say, whereas a cyclone is a wide band activity. A cyclone may cover something like 500, even 500 to 1,000 kilometers in diameter. So it's a large phenomena, whereas the tornado is a comparatively narrow band activity. It covers areas like 100 meters or 200 meters and moves 3 or 4 kilometers. That's kind of thing that a tornado may be like. And then, of course, thunderstorms, downbursts are also very localized activities. So although they have a damage potential, all of them, I would think that for us, it is these winds which occur more frequently, occur all over the country, and cyclones, which are a wide band occurrence with high velocities. These are the two of greater concern to us in our country as designers. Just some pictures. Cyclone, you can notice the circulatory motion here. That is obvious. This is a tornado which has lifted with it a lot of debris, and that's a thunderstorm. I'll just, in the next slides, also very briefly show the structure of wind that is. I was just mentioning that cyclones and monsoony gales and winds, etc., are of greater concern. A little bit about cyclones. We notice here the occurrence of cyclones is shown in these bands globally, 5 degrees to 30 degrees in the southern hemisphere and 5 to 30 in the northern hemisphere. We are here in the cross-hatched form, portion, and so therefore, number of cyclones do visit India. And normally between September and December, while the global occurrence is about 80 per year, we get about 6 per year, mostly on the east coast. But recently, in the west coast also, the activity has been increasing. So I think we have to worry about the west coast as well, a little more than we have been doing. Then, yeah, and this area here experiences 45% of the global numbers. And as I mentioned about the structure of a cyclone, as I had mentioned, it has a very large size, maybe up to 1,000 kilometers. It has high wind velocities, which are circulatory. It brings surges and it brings rain, heavy rain. And that is why the damage potential of a cyclone is very high. You can imagine the energy that a mature cyclone will carry. If you imagine a 1,000-kilometer diameter fan running at 50 meters per second, let us say, and carrying a lot of moisture in it. So obviously it has a lot of lethal potential that a cyclone has, and that is why we worry so much about saving ourselves from cyclones. Next one, please. This is a study that was made by United Nations Development Program, and it is dated, it's 2004. But what it shows is the physical exposure and relative vulnerability to various natural hazards. And earthquakes, India is here. This is the number of people, by the way, here on the x-axis. As far as cyclones are concerned, China has perhaps the greatest numbers. We are next to China, and then, of course, other countries. And floods, India is perhaps the highest affected. China is next. So what it shows is what I am saying, it's like a proof of what I am saying, that the damage potential of cyclones is very high and we are very vulnerable to them. Large numbers of populations are vulnerable to cyclones in India as well as China. Next one, please. Yeah. Now, some simple facts about how wind affects structures. A very simple equation here that I put for you is that the force due to wind can be computed with the multiplication of a pressure coefficient, the pressure that occurs, and the area of exposure. And the pressure itself is half rho v squared. Rho is the mass density of air, unit weight of air. V is the wind velocity with which the exposed area is being impinged. Cp is the pressure coefficient, and A is the reference area of exposure. So this is the simple equation with which you calculate wind forces. The issues here are V and Cp. V is something which is critical. We should know a good or a realistic value of V, and Cp is again a coefficient which depends on a number of factors. I'll just explain to you. V, I always consider as to be the most critical, because it is the square of V which comes into picture in this equation. So any errors in V, even plus minus 10%, means the forces will be out by plus minus 20% almost. So V is critical, and of course the accuracy of Cp is important. Let's go forward. Next, please. Yeah. Next. Yeah. Right. Now, I had shown this slide earlier, and it's only a repeat. this is your mean wind speed, and this is the fluctuating part. Now, the wind speed that you designate as the applicable wind speed depends on one part on the height above ground. On the other part, it depends on the time of averaging that you use. If you use, say, a small time averaging like 3 seconds, you will get a higher average value. But the fluctuating component will become smaller. If you use a longer period of time for averaging, let us say 1 hour, then you will get a smaller mean value and you'll get a higher component of fluctuating values. The Indian code uses 3 seconds as the averaging basis. Some codes use mean hourly values. So if you have mean hourly values, you will get higher values of intensity of turbulence or this fluctuating part. And if you have a smaller averaging value, then you get a smaller fluctuating component. Next, please. Next, please, Abhay. Yeah. Now, the design wind speed that I mentioned, that was in that formula, it can be obtained in the code as a basic wind speed and multiplied by these factors. V is the design wind speed at any height, and it does vary with height. K1 is the probability factor risk coefficient, and this depends a great deal with the exposure of the structure, the life of the structure. Then you have this factor K2. It depends on where the structure is located vis-a-vis the flow of wind. If the wind is flowing over a smooth terrain or a rougher terrain towards the structure, that affects K2. Height above ground, I have already mentioned, affects K2. And the structure size also affects K2. Now, you will wonder why the size of the structure is affecting this factor. The size is affecting because, as I said, the wind velocity, if you look at the situation in space, then the wind velocities are again randomly varying and not exactly correlated. Now, if you average out the wind speed over a large area, you'll get a smaller value. If you average it out over a smaller area, you'll get a larger value. Just like the time that you use for averaging. Similarly, the area that you use for averaging also affects the wind speed that you get. So all that is built into these factors that we are talking of, K1, K2, etc. K3 is a topography factor. It depends on the topography on which your structure is located. And K4 is a cyclone factor, which I will just explain where it is applicable, what the values are. But this then is your velocity V. This is the design wind velocity, which goes into that formula F equal to CPP into A. Next, please. The basic wind speed VB at 10-meter height, averaged over a period of 3 seconds, is given in IS 875 part 3 for the country, which is divided into 6 wind speed zones. There are not 6 zones, but these are the six wind speeds that occur in various areas. 33 and goes up to 55 meters per second. These are statistically reduced values based on the meteorological data for wind. And K1 to K4 can likewise be found in the code. Next, please. Next, please.
Done, sir? Next.
That's okay. I've got it here. The design wind speed is affected by the geographic location. Now, this depends on where you are located in the country. It may be the 33-meter zone or the 55-meter zone. The coasts are generally affected by higher wind speeds. Height above ground has been mentioned, topography, approach terrain, life and size of the structure. These are summary. In summary, these are the factors which will broadly govern your wind speed. Next, please. Let me explain topography and the approach terrain. Now, supposing here the wind is blowing from left to right, and this is, let us say, blowing over a desert or the sea, then you have a certain variation of, of wind speed that you see here. Now, if you then move into a terrain which is somewhat rougher, some trees, etc. are there, some buildings, some trees, and so on. This is rough compared to this. Then this changes. You get a somewhat different variation of wind. And this again is taken into account when you get the values in the code. There are four, I think 4 approach terrains that are given. A smooth, comparatively
Now
rough
only
terrain.
started explaining, right?
Then
No,
there is the, if you are in a city center. Now, if you are in a city center, then of course this will again become narrower like this. Of course, the turbulence in a city center becomes larger. The turbulence here is smaller. So the approach terrain towards the structure matters, and that does affect the values of wind that are taken into account for design. Now here, one shows through this the effect of topography. If your structure is placed here on top of a hill, then you notice that whereas this is the normal variation of the wind speed, it becomes like this. There's a speed up.
ఎవరైనా ఒకటే ఓకే నేను నా వాడికి నాకు మాత్రం
Mr.
Please
Sundar,
mute others.
please mute, please.
All others, please mute.
Okay. Now, if you come downside this hilltop, then you notice that the wind velocity, again, the variation changes. There is a substantial change that is possible. So if you want to build your house on top of this hill, be prepared for higher wind velocities. And if it can become 1.20 instead of 0.8, then the difference in the forces that you will experience will be 1.2 divided by 0.8 squared, 2.25 times. And if you want to be in safer environment, smaller wind speeds, well, this is the location here, downhill side. Here the value at your building level probably has gone down to half the value compared to the normal value. And half means that the forces that you will experience will be 1/4, because they're proportional to the square of the velocity. So that's the effect of approach terrain and the topography. Okay, next, please. Now, as I mentioned, V was one crucial factor, and Cp, this pressure coefficient, is another. Now, you would imagine that this should be a very simple thing, and I don't want to say that it is complicated, but it is not as simple as it seems also. What does Cp depend upon? Let us look at this simple gable building. and let's say wind blowing from left to right, you will get different values of Cp on all these 4 surfaces. And you will get different values of Cp inside. The Cp inside is dependent upon the openings in the building. Depends on what size windows you have, doors you have, what are other openings that you have. And this change here from left to this, to this, to this is because of the flow and the separations that occur as the wind flows from left to right. So that's one aspect, the location on the structure and the openings in the structure affect the value of Cp. So if you're wanting to get the force here, or here, or here, you will get different values of Cp to use. Next, please. It also depends on the aspect ratio, etc., the dimensions of the building, the geometry of the building. What is the angle of the roof? What is the width to length ratio? What is the height to length ratio? All that affects the value of Cp. And also the angle of incidence of wind affects it. So that's why I said it's not as simple as it would appear. There are many factors that affect Cp. Now, one would wonder, the courts of practice do give values of Cp for various kinds of shapes and sizes, and that's a great help. But as I'll mention later, there are also challenges still left, even in as far as Cp is concerned. Next, please. Next, please. Yeah. So geometry, angle of incidence, crucial locations are edges and ridges where you get higher values of Cp, openings. Much is covered in quotes and standards and literature. For short and stocky structures, except, the exceptions are when you have to use or you have to deal with unusual geometries, which are not covered in the courts of practice. Also, most of the time, for different shapes and sizes of structures, values of Cp would be given to you, assuming that the building is standing on its own. There is nothing around it. This is the only building there in the location. But obviously, this cannot be the case. You have other surrounding structures and installations and buildings, and those interfere with your building in question. And that affects the wind pressures and forces on your structure. So that's something which is covered in our code of practice to some extent, but that is a challenge really to try and do more work and generalize things, which is a tough ask. So this is one aspect which remains a challenge if you want to take into account the effect of interference from other structures, because this will vary from site to site. The generalization, therefore, is a difficult job to do. And then I mentioned unusual geometries. Next, please. Well, these are some examples of unusual geometries. You might notice that the straight lines have given way to different forms of curves. And this is the current architectural practice. The structures have become more and more challenging, more and more exotic in their looks, but they do present a challenge to the wind engineer. Next, please. You can go over these slides quickly, where they're just showing different shapes and sizes. Yeah, unusual geometry here again.
This is in India itself, sir. Can tell more
in
about
India.
this.
Yes, this is one of the ONGC buildings. This is a building owned by ONGC.
Where has that been made, sir?
I think in Calcutta, but I'm not 100% sure. I
I
know
think Kolkata.
I know SERC did a lot of its engineering, and Marrow consultants were the consultants for it.
Ji, ji.
And this slide here shows, as I was mentioning about interference. Now, supposing you want to know forces and pressures on this or the response of this building here, then you have these structures all around it, which are interfering with the flow that you will get on this building. So that is there's one factor, one challenge that continues to remain. Next, please. Now, for cases not covered by the codes, standards or relevant literature, wind tunnel studies provide the best option, though prototype field testing also is a possibility, but that is rather expensive and more of a luxury for a designer, because you may build your structure as a prototype experimental structure, but you can't order a storm. So a storm may not hit the structure for weeks or years. So that's a luxury. I think that's only for people who are doing research that you can do this kind of thing. Another route is the analytical approach using CFD. But CFD, again, I think it is still in a nascent stage. It's going on improving every day, the capabilities go on improving all the time. But still, I think it is not at a stage where I would say that it can replace wind tunnels. Wind tunnel, therefore, seems to me to be the forte for finding out effects of wind on a building or a structure today. Next, please. Now, then I mentioned that for stocky structures with larger frequencies and smaller time periods, you can more or less treat them as quasi-static. And much of what is given in the code can be used as factors for it. But there are structures which are more flexible, taller or larger spans, and their time periods are larger, which you normally describe as wind-sensitive structures. For them, a dynamic analysis, which again is covered in the code of practice, has to be followed. Next, please. Just some examples of wind-sensitive structures. We can go over quickly over these. These are all wind-sensitive structures of various types. Some very fine bridges. They are all highly wind-sensitive. Wind is essentially a dynamic component of wind is very important to all these structures. And the dynamic response is very important. Now, for these wind-sensitive structures also, as I mentioned, much of the information is there in the literature or in the codes of practice. But here, I would say compared to stocky structures, there are more gray areas which need to be looked at as far as these wind-sensitive structures is concerned. Next, please. Okay, now I think the time also is about 4 o'clock, and it was supposed to be the time by which I should stop my presentation, but there was some loss of time in between. But the next part, I do not wish to take much time on it because it deals with tall buildings. And tall buildings is something which Dr. Abhay Gupta is going to cover in his presentation. But I'll just run over 1 or 2 slides, and then we can pass things on to Dr. Gupta to make his presentation. Next, please. Next, I think you'll explain all that along wind and across wind oscillation, etc. in your presentation. Next, please. Yeah, the issues I would say, in tall buildings is determination of forces and reactions, oscillatory response, acceleration, which has to do with the comfort of occupant more than I would say structural issue. Then you want to know pressures, load on the envelope for the design of the structure as well as the envelope. And if vibrations are unacceptable, then control of vibrations is another issue using different kinds of dampers. Also, if the forces that you're getting on the structure are unacceptably high, there are ways and means of reducing both the static component of forces as well as the dynamic component. The other issue, which is important, I think, is interference is one that I've not listed here. That is an important issue. But wind environment near the base is something else that we need to study carefully, because when you are next to a tall building, you can experience uncomfortable and even seriously damaging kind of wind flows. And therefore, the wind environment near the base requires a study. There's a slide at the end, Abhay.
Sir,
If I show that last slide, I think that's... Yeah, these are reduction in wind loads. That's, yeah. And that's for reducing oscillations. And
last is this one, sir.
last is the next 45. Yeah, that one
Yeah.
shows, a model placed in the wind tunnel for studying the near base environment. Okay, then with your permission, I'll stop my presentation here because I think you must be looking forward to Abhay Gupta's presentation on tall buildings. Thank you.
Okay, thank you, sir. Before Dr. Abhay Gupta starts his presentation, a little bit of CV. Dr. Gupta, he has graduated in civil engineering in 1981 and then ME Structures from SGSITS, PhD from University of Roorkee, which is now IIT Roorkee, in 1996, in the area of aerodynamic interference in tall rectangular buildings, wind tunnel studies. He has more than 40 years of experience in civil engineering in different kind of activities, from structural design as well as teaching and research in various institutes. Dr. Gupta is also the director of Skeleton Consultants Private Limited, which has its offices in Delhi, NCR, Indore, and Bangalore. Earlier, he was involved with EIGEN Technical Services Private Limited, ERA Building Systems Limited. He was the faculty of SGSITS Indore from 1984 also. He has a huge list of works which he has implemented, out of which the best one perhaps is a 351 feet high Lord Shiva statue at Rajasthan, India, which has won several prestigious awards for structural design and construction, including ACI International Award, ICI Award, ACCE Simplex Award in 2020-21. The statue is a hybrid structural steel plus concrete structure and fourth tallest statue in the world. Otherwise, also his activities ranges a huge gamut, which might be quite long to go deep into it. And he is affiliated with various professional bodies. With this, Dr. Gupta, we have cut short your CV. Otherwise, it will take a little bit of time. And so now over to you, sir, for your presentation. Thank you.
Thank you so much, Mr. Ghosh. I'm honored to deliver this particular talk on Insdag platform. We all have known Insdag since long and how well they are contributing towards the construction of steel structures in this country. I hope I am audible. I am audible?
Yes, sir. Perfectly right.
Okay. With due regards to Professor Prem Krishna, who has been continuously mentoring me, inspiring us, I got in touch with him in 1991. And since then, he has not left me alone on all my professional assignments and even my personal journey. So thanks a lot, sir, for all your blessings. I can see in the audience Dr. Harshvardhan Subbarao, a stalwart bridge engineer of this country. I also see Dr. P. Harikrishna. Dr. P. Harikrishna is a person who is himself has drafted this code 875 part 3. So his presence certainly will help me if there are any unresolved queries which audience raises. There would be many more people, I'm sure, who are well known in the field, but to my direct contact. So I welcome you all and I seek your permission to start this presentation. I'll just share my screen. Just a moment, sir. Somebody else. Is this seen?
Yes, sir. We can see it.
You can see the first slide. Okay.
Yes, sir. Yes, sir. It's okay.
Thank you. When we say tall buildings, many of these buildings immediately come into our mind, which as a civil engineer, as a structural engineer, most of us have heard about these buildings, though unfortunately World Trade Center, which is third from right, no more exists. But then there are many more who are going to be added soon in this list. As on date, we are only having this 868-meter tall Burj Khalifa. But then I have heard that people are planning 1 kilometer, 1.6 kilometer high buildings. So this construction of tall structures, tall buildings on Earth's surface is continuous for many reasons. For many reasons. Some of them are buildings and a few of them are structures which are not habitable buildings. Some structures are there. In India also we see now buildings in the range of 200 to 400 meters. We have more than 150-meter buildings. We have several now in Delhi NCR, in Bangalore, in Mumbai. So this is an era when the advancements and the developments in our codal recommendations, our knowledge, our researches, our material to be used, all those should continue. So this is very important that we discuss all these things. What exactly is a tall building? So somewhere it is well defined that a structure that because of its height is affected by lateral forces due to wind or earthquake to the extent that the forces constitute an important element in structural design known as high rise or tall building. Very simple definition. Tall structures are wind sensitive and prone to large wind induced vibrations. Wind forces on a structure are estimated considering it as an isolated structure, that is a standalone condition. Whenever we analyze, we assume that only this particular building is existing. The basic study. The standard codes of practice suggest that one should go for the internal studies for unusual structural shapes, as many of them have just now been shown by Professor Prem Krishna. We don't get the prismatic rectangular box type buildings. We have architectural fantasies, some of them I'll show, and locations for which sufficient information is not available in the standard code of practice. The standard code of practice will provide you the data and the recommendations for the standalone standard prismatic cases. For everything which is beyond that, we need to go to the specialist literature experts, wind tunnel studies, and maybe some other analytical tools like CFD nowadays to some extent for the preliminary studies. Issues are like the structure of approaching wind is important parameter, as very nicely explained by Professor Prem Krishna, that what are those complications of the approach wind flow, and each one of those parameters play an important role in deciding the wind pressure and then wind induced response. Choosing the correct design, wind speed and profile is very, very important. Building response analysis, whether static analysis, static response or dynamic is also important. Beyond a certain range, dynamic response, and beyond a particular type of the structure, like bridges, slender bridges, when their deck, which is quite thin, undergoes torsional flutters, although dynamic analysis becomes very, very important. Design issues, interference effects, as Sir said, and we are discussing that buildings do not exist in standalone. They are always with a family. Chote bade, all type of structures would be there around it. And when they are there, there will be change in the approach wind flow and that will affect the response. So that is called as interference. And it is very important to study that. IS 875 part 3 approach. So for design issues, further, one approach is codal approach, IS 875 Indian code. Similarly, there are other country codes also. Provisions of IS 16700. This is a new latest document which is for the construction of safety of concrete, tall concrete buildings. Its title is like that. If suppose in future there is a tall steel building, then there may be another code which we will have to prepare for that. And some exercise on that has already started. This 16700 is for concrete buildings, but provisions of wind are there, some provisions, we'll see them. Wind tunnel techniques, very, very important tool and very authentic, providing, if I don't say very economically, but in a reasonable cost as compared to the cost of the project, we get good information. Computational fluid dynamics analysis, for some preliminary studies, this can provide a very good, at a lower cost. Every time we can't do wind tunnel testing for 10 different cases. So which of those cases which we take for the wind tunnel testing can be converted by CFD. But CFD has not reached to a level where we can solely depend on it only. It will not be able to replace wind tunnel as of now. Limitations and the way ahead for the practitioner. Some parameters related to the wind. Movement of air on Earth's surface is called wind. We all are familiar with this definition. When there is a temperature difference, pressure difference from one point to another, whatever flows is called as wind. Objects on Earth's surface like trees, structures, etc., they retard the flow. Anything above the surface of the Earth will retard the flow. Wind speed varies from 0 at surface to a maximum at the gradient height where the effect of obstructions has vanished. This is very important, and for every wind engineer, for every structural engineer, it is very important to read those few initial pages of the code or any other book. I'll show you some names where this particular phenomena has been explained. Boundary layer flow, how the boundary layer develops, how the flow varies from 0 to a maximum free flow after some height, and how does that will affect the structural response. Very important. The variation of wind speed from 0 at ground to a maximum of gradient height is called as boundary layer flow. All our structures, for a structural engineer, boundary layer flow is important. Aircraft people, space vehicle, and they are beyond the boundary layer where there is a parallel flow. There is no variation. So that's a different ball game altogether. We are not into that. The approach flow to any structure inherits the characteristics of obstructions it has passed, like size, shape, scatter, density, everything. So whenever a wind flow crosses the obstructions and reaches to a building, it will inherit several things. Inherit means the eddies which have generated in shape, in size, in plane. There will be eddies in horizontal plane. There will be eddies in the vertical plane. There will be small eddies. There will be big size eddies. all those mixed together, depending on what kind of the structures it has overcome, will reach to the building. And that is what will decide the nature of the wind which is reaching, and it will decide the response. Terrain category is the description of ground surface with respect to size, shape, and scattered density of the structure. Variations in terrain category are there. Actually, in our code, if you see, as sir has told, there are 4 terrain categories which have been defined. Terrain category 1, 2, 3, 4, depending on the roughness or depending on the structures present. You can read the description. I'm not going into those details, but if there are any queries, we can address. But worldwide, there are 6 to 7 categories in different codes. People have used up to 7 categories. Different. Mean wind speed depends on averaging time and terrain category. So terrain category will decide the retardation, mean wind speed, and the boundary layer height, and therefore the profile. While the averaging time, as sir said, that if it is a 3-second averaging time, if it is a 10-minute or 600 second, or if it is a 3600 second averaging time, some countries use hourly, then some use 10-minute. So depending on the averaging time, the basic wind speed, mean wind speed changes. Wind is completely defined by mean speed, turbulence intensity, turbulence scale, and energy spectra. These are the 4 parameters. If you know about these of the wind which is approaching a building or a structure, then we know, more or less we know about the wind there. Tall, very confusing word, or it is a qualitative. There are 2 people standing, one will be tall, another will be short. Now it is between them. When a taller person will come, the another one will become tall. So it depends on whether I am standing by the side of Amitabh Bachchan or I am standing by the side of some other actor who is comparatively short. So it's a matter of feeling. Now in these 2 structures, B1 and B2, both having same height, which one will be called as tall? Very difficult. Whether height is a critical parameter, what is the role of plan dimensions, whether h by b should be considered as aspect ratio, or whether h over square root of bd should be considered as aspect ratio. This is being discussed worldwide, and probably maybe in discussion we will see, but in our code we are having h by b as the aspect ratio. Role of natural time period and frequency, the dynamic characteristic of the structure, and tall, whether in terms of looks tall or in terms of behavior tall. So basically we are in terms of behavior tall we are talking. You'll see now, I'll show you some of these structures. Now this is a plan of a tall building configuration. You can see one tower on the left hand side, tower 1, which has got 3 arms, Y shape. And tower 2 is a compact, and both are connected by a bridge. This is the model of that. Extremely complex. And you can see on the right side, if you see, there are small pools, those kind of jacuzzi pool or some kind of pools in the balcony, cantilevering balcony. So our imagination of architects is really amazing, and we structural engineers have to deal with them. This is a building in Mumbai, Lodha Bellissimo, 204 meter tall, 64 stories. And I had the privilege of, I was involved in the wind tunnel testing of this along with Professor Prem, Krishna and team. We did this. This is a building in plan in Kolkata, Uniworld City. This is only 16 meter wide in the middle and about 19 or 20 meter at the end, and 95 meter face width.
इतना जगह दिख रहा था यहाँ पे तो रोका नहीं गया.
Please mute yourself. So in pursuit to give more open exposed areas to the flat owners, the architects have started planning these shape of buildings, thin and wide in plan. And these buildings are highly vulnerable to the wind response. Some of the buildings, the left one is a building in Noida, 24 floor, 101 meter tall for Gas Authority of India Limited corporate tower. So it is an I-shaped plan. And over that on the top, you see a 20-meter spire going further up. A internal testing was done by SCRC Chennai. Dr. P. Krishna himself did that. And we did the structural engineering of this building, our firm. On the right side, if you see a building like stacked boxes, this was an imagination, this was a concept elevation of a building proposed in Mumbai. I don't know whether it has taken shape. So all these possess a lot of challenge and they cannot be solved with the code only. But certainly to begin with, we have to take the some preliminary calculation from the code and then move ahead further. Now, some basic things, flow pattern around building. So when there's a building, these are the plan of the building. So how the flow separates at the corner and then the wake area is generated. There is a separation zone. This flow pattern, which is around a building, as per its corner shape and all that, generates a wind pressure like shown on the right side. At the separation corner, there is a high suction. You can see 0.6, negative 0.6. On the back side is negative 0.2. So there is a weak wake. There's not a very strong wake zone on the back side. For some reason, in other building will be stronger. On the front side, where it is 0.7, it is a pressure which is more in the middle. And as you go toward the edges, because the flow is separating, so the pressure reduces. Once you have understood clearly, or more is the understanding of this kind of flow pattern around various shapes, better is the understanding about the surface pressure which gets generated, and better is the, you can say, understanding of the behavior of the building. If there are two buildings placed like this, one upstream, one downstream, then the flow separated from one building leaves and strikes to the other downstream building, and then again there is something, some change happens in the flow, and the pressure contours around that as measured by a scientist, a researcher earlier in 1991, like this. Some cases where the buildings are not perfectly rectangular block, but they have spaces, they have height ups and down, they have gaps below. Some nowadays we see metro passing through the building in the middle. Correct? Just a moment, huh? Please, there's an urgent call. हाँ योगेश जी. हाँ वीरेंद्र, ठीक है. हाँ मेरा कार्ड इसके पास है. ठीक है, थैंक यू. हाँ हाँ ठीक है. Sorry. So for some reason the building shapes, heights, cutouts, openings are there, and they alter the wind flow pattern. And these flow patterns are localized phenomena in some areas, but it in turn affects the either the cladding design, facade design, those local member design, and sometimes foundation also. Like this. It is very important to visualize or to see the wind flow pattern. All these cases cannot be covered in the code. Vortex shading is a very common phenomena and is very important to understand. When the wind strikes the surface of the building, it displaces it on either side. So at low speed, vortices are shed symmetrically in pairs, due to which there are no vibration in the transverse direction. But at high speed, vortices are shed alternatively from both the sides, from left and right. So when the vortice is shed, there is an eddy which is formed and it is releasing the wind from one side. Then there is a suction created and the building is sucked on that side. At the same time, then the vortices will be shed from the other side and the suction will generate on the other side, and alternating suction condition will generate, and building will experience a pressure or force from left and right side alternatively, and this is responsible for generation of the across wind response or across wind force in the building structure at a particular speed. Very important to note this elevation. It is not that like in plan only the wind flow pattern separates, but in the elevation also there is a 3D behavior. On a tall building, up to about 80% of the height, The wind flow is 2D, means the planar. It just separates from the two sides, left, right. But as you go near the terrace, in the upper portion, there is a separation of the flow in the vertical plane also. And that alters the wind pressure near on all the surfaces, all four sides as well as the roof. And then there is a, can say, change in the response. It affects the entire response because more fluctuation at the top means it affects the foundation level in terms of its height from the base, means the lever arm increases. So it is also important to understand how the flow pattern will be there near the roof. Various design issues. Just a minute. Types of wind design it is, and beyond the routine, environmental wind studies are conducted in general, which also include the wind on pedestrians, motor vehicles, and architectural features such as fountains. Because around a tall building, the wind flow pattern gets modified significantly because of the downwash. The wind attacks the building and from the surface it goes down, and then it affects people who are walking around. Wind loads for facade, that is a very important area. Nowadays, very costly facades are used in the buildings, and it is very important to use proper material and design. We have seen in many buildings, entire facade gets collapsed if some small area is not properly done or taken care of. Third one is wind load on structure, to which we are discussing today. To determine the design wind load for designing the lateral load resisting structural system of a structure to satisfy various design criteria. The structural response is divided into two parts, along wind and across wind. Along wind means in the direction of the wind. The response of the structure in the direction of the wind is called as along wind response, and the response in the perpendicular to the wind direction is called the across wind. Now you will say, is it that wind only flows in one direction? No, wind flows in many directions, or wind vector can be in other directions also. But one thing is sure, that the resolved component of wind in X direction and in Y direction will majorly affect the lateral load resisting system, which is oriented in those two directions. And a structural system in Y direction will not resist any force which is developed or generated in the X direction or due to X direction wind. So both are independent. There may be some, you can say, cross correlation, but for all practical purposes, we consider them to be separate. It is a mean along wind response. It is a mean component in the direction of flow, and over this is superimposed the fluctuating component, which has a peak value and RMS can be calculated. I'll explain it more. An across wind response or lift force, it is zero mean component, because as such there is no externally applied across wind force. It generates because of the wind flow, and it generates because of the geometrical shape of the structure. So it generates on either side symmetrically. So there is no mean response, but there is a fluctuation and fluctuating response. So unlike along wind response, across wind response is only fluctuating, while in along wind direction, first there is a since mean force. So the entire building structure, according to its stiffness, gets deflected. Just ठीक है मेरा लेक्चर चल रहा है. So under the mean wind force in the along wind direction, as according to the stiffness, according to the dynamic characteristics, the building gets deflected, drifted, swayed in one direction, and that is a mean response. But since there is a fluctuation in wind in that direction, so then about that mean deflected position, the building starts oscillating. Building starts oscillating. So there is a mean plus there is a fluctuating component, basically. Across wind vibrations are usually greater than along wind vibrations for buildings of higher heights greater than this one. For very tall buildings, which are comparatively flexible, the vortex shedding is predominant and some more phenomena, and we get a crosswind response also, a significant value, which may sometimes be higher than the along wind response. This explains the vortex shedding. This is a flow visualization image on this left side. And if wind velocity versus crosswind response is plotted, then due to vortex shedding, there is a phenomena which occurs. Lock-in means the resonance lock-in happens at this particular frequency, which is n is equal to SU over B, where S is the Stroud number. So depending on the Stroud number, depending on the wind speed, depending on the face width of the building, this particular condition arrives at, in a structure at a particular speed, and there you can say violent crosswind vibration may happen. So this sometimes becomes very critical. To study all these things, as a practical engineer, as a design engineer, there are two methodologies which are available. One is either we use an IS 875 approach or we go to the wind tunnel tests. And our scope today will be to go through IS 875 only, that approach, and that to the new code. And maybe the time which we have may not permit us to go through in detail, but certainly I'll be able to take you through and give you an overview so that at least you know about some of the important things, and then come back with your queries when you work on them. 875 has two ways of calculating wind load. One is static analysis, one is dynamic analysis. The static analysis consists of following steps. First, you have to work out the basic wind speed, then design wind speed. Now, I'll open the code after few slides and will tell you one important thing with regard to the design wind speed. As sir has told, the basic wind speed VB you have to take from the map. The map now is you have to refer the new map. New map means the map which has been published in NBC 2016. Many of you are not aware of this development, that subsequent to the publication of 875 Part 3 2015 version, there was a change because of some meteorological station studies and a recommendation, and the wind map was modified, which was published later in NBC 2016 wind load part, and then it was also published by BIS as an amendment 2 to the IS 875 Part 3 in June 2020. I'll show you that amendment also. So that is one thing. Secondly, when you convert that to design wind speed, first is from the VB, you multiply by K1, K2, K3, K4 according to the situation. And then there is a PZ, design wind pressure, that you have to calculate. And for low-rise structures, we convert that PZ into PD. However, in case of tall buildings, there are two changes. One is the K2 factor has to be taken, not from the table which has been given, I'll show you, but from an expression which has been given. And this conversion of wind pressure using KD, KA and KC is not to be done. They are incorporated in the Gust analysis procedure itself. So these are the things to be taken care of. Calculate surface wind pressure on building face and applying in analysis to get overall forces, or calculate overall wind force using force coefficient approach and use in analysis for main frame and foundation. There can be two approaches. One approach is either you calculate the pressure using the pressure coefficient approach and multiply by the areas and get the force, or you can even get the overall pressure, overall force from the figure 4 of IS 875, which I'll show you just now. That in the first approach, in the pressure coefficient approach, the force is obtained like this is by the force coefficient approach. This is the overall force which is taking care of pressure on windward phase, pressure on leeward phase, and also the internal pressure if there is anything generating in all complete. So you can directly use this CF value as given. Otherwise, in some cases, you can use the CPE on all surfaces, CPI, do CPE minus CPI, use a CF, force coefficient, use a pressure coefficient, and then obtain effective area multiply and then obtain the force. In my opinion, for tall buildings, using the masonry walls and having several internal partitions where CPI generation may not be much, you can say, effective or proper. There are multiple level of the floor slabs also. So in my opinion, for tall buildings, force coefficient approach also only should be used and not the pressure coefficient. Only in case of cladded high structures, which doesn't have internal partitions and which doesn't have internal floor slabs, floor levels, you can use the CPE CPI approach. This is the figure 4, where depending on the plant dimensions and height and all that, you can get CF. There is one more chart for the smaller buildings. This one. Beyond that, dynamic wind effects is the second part. This was for the static. In dynamic wind effect, there is a condition laid down in IS code. I'll just show you. Okay, we'll go to the code that time. I'm just taking you. So we can have the 875 along wind response, which is a gust response factor method, which is based on Davenport's gust slender line-like structure approach, which has been modified. And this is the basic of the Davenport's gust factor approach, where the response of a tall structure in along wind direction is composed of X bar, which is mean response, plus RMS into peak factor. Whenever there is a you can say fluctuating phenomena, anything, not wind, but any fluctuating phenomena, from statistics we know that if you plot that, there are certain statistical derivations you to take from there. One is the mean value, another one is root mean square value, another one is the peak factor, those kind of things. So and standard deviation. So when you use that, the resonant response, mean response, peak factor, and the RMS value, then you get the means the fluctuating part multiplied by a peak factor, which is generating the response, add it to the mean response, and you get the maximum response. That is the maximum along wind response. Now, how to calculate these things? The peak factor depending on the natural frequency of the structure. How to calculate the other thing? So when I divide this expression, X max is equal to X bar plus this is divide by mean response, I get this thing, which is X max over X mean, ratio of maximum to mean, which is called as a enhancement, which you can term as dynamic amplification, ratio of maximum to mean. That is called as gust factor G, which will become 1 plus this thing. So G is the gust factor approach. So if you know the value of G, you can directly multiply that by mean response, and calculating mean response is quite simple. So mean response into gust factor G, you get the enhanced response. Simple. So Davenport gave a very simplified version of this, that how you can calculate. But in principle, the fluctuating response composed of two things. One is, it is because of the fluctuations in the wind. So when there is a fluctuating wind approaching or attacking a building, then it will also make the building to fluctuate. Now the building will fluctuate in two ways. One, because there is a fluctuating phenomena, so there will be several frequencies and corresponding amplitude will be there. We all know that. So if we plot that frequency versus amplitude, we get the spectra. Means at a particular frequency, you will get a higher amplitude in that wind, means more energy there. If that corresponds to the building frequency, then for that particular frequency, there will be a resonance of the structure, means more amplified response will be there. So near to that particular frequency, you get amplified response, and beyond that, you get a normal fluctuating response. So there are two components of this fluctuating response. One is called as B here in that expression, which is background response, which is normal fluctuation, and one is R, which is resonant response. It is because of the matching frequencies with the wind, building in wind. So if possible, designers try to keep the building frequencies away from the wind frequencies to safeguard the building. Some of the expressions there. Here you see the blue part. Which building is required to be analyzed for dynamic? Buildings and closed structures with a height to minimum lateral dimension ratio of more than 5. तो अगर 5 से ज्यादा है तो आपको डायनामिक एनालिसिस करना है, irrespective of the plan other dimension. Buildings and closed structures whose natural frequency in the first mode is less than 1 Hz, means natural period is more than 1 second. Natural period more than 1 second means building is flexible. 5 second की building ज़्यादा flexible as compared to a 2 second building. 1 second से भी कम अगर time period है किसी का तो वो बहुत rigid है, stiff है. So if it is so, less than 1 second period means frequency more than 1 Hz. वो बहुत rigid है, तो then dynamic response नहीं होगा. This is the code is saying. So code says ये दोनों में से एक भी condition अगर आपकी हो रही है satisfied, तो you have to do the dynamic analysis. The natural period calculation formula, though again this is an empirical formula, and long back we used to have a formula like 46 by H, 57 by H, or 75 by H. Those were from the empirical, from the, you can say, study on several buildings and then plotting them. Then what height of building has what natural period under the ambient vibrations from there. Now, as compared to the, now people have a confusion. Earthquake code says some other natural period formula. Wind code says some other. And many people come to us asking, sir, should we not use that one? It has got 3 formula. It has got more detailed information. No. Why? Because basic philosophy is different. The wind design philosophy is elastic, while the earthquake design philosophy is non-elastic, or you can say it is into the non-linear zone. In earthquake design philosophy, damage is allowed and expected because earthquake will happen once in few years. रोज नहीं होता. But wind is a phenomena that if not the maximum wind, 50% of maximum wind will be blowing every day or maybe once a month. So the building or structure has to remain elastic. So when it has to remain elastic, the natural period of oscillation for wind design will be different than that for the earthquake design. In earthquake design, the natural period will change immediately as the shock occurs. So we are using this one only for the wind. However, many designers, they say when we model the structure in ETAP software or some other software, we get a higher value of natural period. Means we get a more flexible building there. And maybe the design becomes more economical. But certainly, unless and until that is accepted by everybody concerned, we cannot go with that. We have to abide by the code only, IS code. If preliminary studies indicate that wind-induced oscillations are likely to be significant, investigation should be pursued with the aid of analytical method or if necessary by means of wind tunnel test on model. Across wind motions may be due to lateral gustiness of the wind, unsteady wake flow, for example, vortex shedding, negative aerodynamic damping, or due to a combination of these effects. These crosswind motions may become critical in the design of tall buildings or structures. Motion in the direction of wind, known also as buffeting, that is a long wind, are caused by fluctuating wind force associated with the gust. The excitation depends on gust energy available at the resonant frequency. The eddy shed from an upstream body may intensify motion in the direction of wind and may also affect crosswind motion. This is the interference. Some more points, but I'll share this presentation with all the participants through Insdag, and then you can very well study all these things. The crosswind motion, up to the last version of the code, we didn't have any procedure in our code. Some other country codes were having, now we have also incorporated. And since there is no theoretical formulation for the crosswind force, directly analytical, so it is whatever has been given in the code is based out of the experimental results only. So when you see this formula, they have been drawn out of the spectrum, the power spectra of crosswind force, which has been measured by the actual forces, actual experiments in the wind tunnel testing. These things will skip right now. This is the crosswind motion power spectra, and from where you have to pick up the value corresponding to the dynamic characteristics and the wind speed of your structure, and then put into the formulation which has been given and obtained the value. That's a mechanical an Excel sheet exercise primarily. But if there are any issues, then we have solved the examples also, which I'll share with the participants so that more clarity would be there rather than explaining them all here. Compilation of some of the worldwide different code along wind method procedure, but not relevant example. This is how the pressure distribution varies on the tall building surface on different sides, front, sides, and back. Now we will come to our code and what are those critical points which have been changed. In fact, this code was released in 2015 September. Then there was an amendment issued in April 2018. Primarily, it was not an amendment, it was a correction document, long 8 pages document. Several typing mistakes were there, which have been mentioned in this. And we hope that when there is a next version coming up, then all these are incorporated. But any user must take care of these amendment 1 issues of typing and put the correction marked in your copy. Then amendment 2 came in June 2020. Primarily, the most important amendment was change in the basic wind speeds. Then came IS 16700 2017 criteria for structural safety of tall buildings. So these are the important documents we'll see. Background I'll give you just for information. This is also printed in the IS code itself, but generally we don't read this particular thing. The standard was first published in 1957 for the guidance, and it was a single document. There were no parts. In its first revision in 64, the wind pressure provisions were modified on the basis of studies of the wind phenomena and its effects on structures undertaken by the special committee. In addition to this, new clauses for wind load for butterfly type structures were included. Wind pressure coefficients for sheeted roofs, both covered and sloping, were modified. Seismic load provisions were deleted. Separate code have been prepared, and metric system of weight and measure was adopted. And then in the next revision, 87, 5 parts were there of this IS 875, which was loading code, which we know as on date, and we are now dealing with IS 875 part 3. So this standard deals with the wind load to be considered when designing buildings, structures, and components thereof. In this current revision, if you see, the committee recommends the following modifications. Aerodynamic roughness heights for individual terrain category have been explicitly included. Earlier, 4 terrain categories were there, but roughness height was not indicated. Now there are roughness heights which have been indicated. A roughness height means an average level of the obstructions in that particular terrain category. So it is like 0.002, 0.02, 0.2, and 2 meters. The previous classification of structures into B and C classes has been deleted. Earlier, the table 2 contained, it was named as terrain height and size factor. Now that size has been removed. B and C. Now it is only for A, and for size there is another factor which has been introduced. the value of K2 factor corresponding to previous class, A type structure only are there. An additional modification factor termed as importance factor has been included for cyclonic region, that is K4. Some empirical expressions have been suggested for height variation of hourly mean wind speed and also turbulence intensity in different terrain. This is what I am saying. For dynamic analysis, we consider hourly mean wind speed, and for that the K2 factor has to be taken from the relation, this expression, and turbulence intensity variation also has to be taken from that. Provisions to account for effect of directionality, area averaging, and correlation of pressure on the design wind pressure have been included, KD, KA, and KC. Guideline to account for the wind-induced interference for tall building. This is an important development. Since many years, the interference phenomena has been studied in our country. Several PhD works have been done, including mine also at Roorkee, and the results have reached to a level where those can be codified. So some guidelines have been incorporated. It is, however, recommended guideline to account for interference, and however recommended to carry out detailed boundary layer wind tunnel tests /CFD, computational fluid dynamic studies, for the final design. Here CFD is not for final, it is only for the preliminary, as I explained earlier. In the Gust factor method for evaluating along wind response, equations have been suggested. Earlier there were charts. So while reading the charts, some error may occur. So now there are expressions for all background factors, size, and people have converted them into proper algorithm or Excel sheets so that the calculations have become easier. A method for computing a crosswind response of tall buildings and lattice towers, which is in line with some of the international codes of practice, have been included. So these are some of the very good developments which have taken place in this version. Many of our young designers who use software for the design, in these softwares there is a command to generate automatic wind forces. And I have heard that the wind force which is generated is being applied at the diaphragm in the building. Actually, in my opinion, this is not correct. Earthquake force is generated on the mass center, so it is okay to apply it over the diaphragm. And then it gets distributed according to stiffness. Whereas the wind is generated on the exposed surface area, and from that surface area, it gets transferred to all the elements through the lateral load resisting system according to the area, tributary area. The force generates according to that and resisted. Now, it is not good to apply the wind force on the diaphragm, because if I apply the wind from left side or right side, then if it is on diaphragm, then the same effect would be there, more or less. But if I apply the wind force on the exposed face, if not on the entire surface, on the beam column junctions, as per the area AE, you can calculate and apply on each node, then that will be a correct behavior and correct analysis. Okay. So that is my analysis and my recommendation for that. Maybe that can become a discussion, but I have asked my people, the engineers who are working with me, to do the analysis like this, and they have seen the difference and the correct values. So it is good always to do a surface application, not the diaphragm action. I'll just open this code. This is the amendment 1, but more than amendment 1 is the code itself. Now in this code, besides all this map has been replaced. I'll show the new one also. Here you can see here this terrain category. In each category there is a roughness height which has been included. And then when we come to K2, K1 factor, it is as it is. This table gives the K1 up to 100 years of the mean probable design life, but in some structures you are having a longer life, then there is a procedure given below for calculating the K1 for a 200, 300, 500 years of design life structures, as we did in case of the Lord Shiva statue at Nathdwara, which has been designed for 250 years of life. This K2 table is for static analysis, low rise, high rise, but static, which is now only height versus the K2 factor. But if you see our hourly mean wind speed, I don't know whether this is, yeah, now you can see it. Vz at h height is K2I Vb. This K2I is to be calculated by this formula and not from that table. That is one thing. Secondly, VZD, you see here K1, K3, K4, and you get this value. VZH, you multiply, so K1, K2, K3, K4 are here, it all. Turbulence intensity, again empirical relations given for all the four categories. These are to be used for Gust factor calculation in dynamic analysis. And here 0.6 Vz square, then Kd, Ka, Kc, this is for the static analysis. But when we go to the dynamic, you don't have this one. You directly get Pd as 0.6 Vz square. I hope I am sure I am correct, Dr. Hari Krishna. This is a confusion to many people.
Yes, sir.
So from here, we move on to that part which I was saying about the force coefficient method for static analysis of tall buildings. Here, force coefficient for clad buildings 742. So here we should use this procedure for calculating the CF and we can obtain the force on each level. Coming down to the relevant portion, that is the, I'm not touching lattice towers. I'm also not touching interference effects today, but this is a good read for interested people. And there is a you can say recommendation which has been included in this. But on the tall buildings, here. So these are the two conditions, any one of which. In general, the following guideline may be used for examining the problem of wind-induced oscillation. Any building or structure which satisfies either of the above two criteria shall be examined. But then there is a note, if you see, the fundamental natural period may be established by experimental observations on similar building, experimental, mind well, not the software generated, or calculated by any rational method of analysis. Now in the modeling, the whatever time period you will get will be depending on the accuracy of modeling and what all components contribute to the stiffness. That is the thing. Because we model only the wire frame and there are masonry walls and other things. So generally I recommend to use this empirical relationship. But for framed building this, and for all other buildings this, which is also there in 1893. The one which is intermediate expression is not there. This particular diagram, you see the recommendation on interference factor, we are not touching today. But once you read, if you have any queries, you want to understand more, we can certainly discuss. These notes, all these 1 to 9 should be read. 9 number is in assessing wind load due to such dynamic phenomena as galloping, flutter, overhanging, in the absence of the required information, either in the special publication or other literature, expert advice should be sought, including experiments on model in wind tunnel. So for anything which is not regular and which is important, critical, wind tunnel testing should be done. We got the Lord Shiva statue wind tunnel testing done at Sydney in Windtech. We went there, Professor Prem Krishna was also there. We saw the entire testing sitting there itself, understood the analysis, and then very happy, and then designed. Dynamic wind response, this is the entire method, which is again, which starts like Fz. Same, this part is static, except that now the PD is different. Now it is see 0.6 Vz d square. There is no, you won't say have that any in between Pz. There is no Kd, Ka, Kc to be used. And then multiply by G, Gust factor. This Gust factor calculation is the entire Gust factor approach. Okay. So this is the procedure for calculating the Gust factor approach. With some typing mistakes in this. This is quite simple. If any queries are there, we can address, but otherwise it is formula based. One by one, you can calculate the factors, put in this expression of G here. This is the form expression, and then you can get. For people who understand the foundations of machines, there is a term called mechanical admittance. For people who are also work with the vibration, theory of vibration, that mechanical admittance is nothing but the same thing, G, Gust factor, matching. Both are similar. Dynamic amplification due to fluctuations is the Gust factor. As I explained, the across wind response, the section gives method of determining the equivalent static wind load and base overturning moment. आपको दो चीज चाहिए. You need equivalent static across wind load and the base moment for a rectangular cross section. Now, for the across wind response, one very typical thing, since this is an experimental based determination, this whatever you see here, this CFS is nothing but the this only thing is required. Rest everything you have. CFS actually. Crosswind force spectritis. This is the only thing which you need, and this is obtained from the chart, and that chart is specific to that shape. That chart is specific to that terrain category. So if there is anything which changes, if my building plan aspect ratio changes, if my building shape changes, if my terrain category changes, then this will not provide me the, I will not say correct, this may grossly misguide you. May grossly misguide you if my CFS values are not for the similar structure. So if you see here, these are for HBD ratio 611 or 911, 611 to 911. Now very rarely you will find a building perfect square and maybe lying in this range. But if it lies in this range, it's okay. You can use it. And wind flow like this, square, no problem. Coming down to the rectangle, 612 and 621. Now that's a very interesting thing here. Same building, when the orientation is like wider face is facing the wind, it has got a peak at around 9 ratio of V by FCB, which is reduced velocity, you can say, reduced frequency, velocity normalized with respect to some dimensions, but there's a peak of at 9. Whereas the moment you change it, there is no peak. It is going like this. Maybe it flattens beyond this, because to conduct an experiment beyond this is very, very difficult. Very difficult. So if your building is not here or here, you can't interpolate. This is another thing, danger. You are not allowed to interpolate between these, because the results will be different, very different. But anyway, if there is any building which is liable to, which is expected to perform in a crosswind direction, you have to go to the wind tunnel testing. There is no other option. You should go. You may estimate something, but there is one thing, some structure which are not too tall, if I am having an along wind force, at the same time there will be a crosswind force generated, and when there is a crosswind, the wind is in the perpendicular direction 90 degrees, there will be a crosswind force in the other direction. Now code says apply the along and across wind together. Okay, now you can apply, but along wind in cases which are not tall, flexible, and not having water shedding vulnerability, will always be dominating than the across way. So combining may not be very, you can say, may not significantly alter your design. I'm talking about the practical. If it's a research problem, do everything. I'm talking about the practical approach. That after all, you as a design engineer, you need to understand what is going to affect your structural design. You need to identify that. And for that, best you must understand the phenomena, that after all, which factor, which condition is going to affect my structural design. Unless and until the design is going to be proof checked by somebody who is not as practical. Sometimes the designs are checked by IITs and other academic institutions, and probably some professor may really insist you to do that because they have an habit of doing some research. So that time you have to convince them or perform that analysis like that. But otherwise, practical approach has to be adopted for a building which is not really tall, and then this is the change in the zone. Next document that is important, which you all must refer. This is the Amendment 1, which was published on 1st April 2016, 8-page document, mostly corrections. So please do that. Next is Amendment number 2, where mostly it is replacement of provisions from NBC 2016, because those all changes were done in 2016 NBC, and then this amendment was issued that please replace this as only that much. This is the zone table which we just see. If you compare this table with the earlier one, in some places the wind velocity, the basic wind speed has been jumped by one zone to more than 2 zones, right from 39 meter per second to 47 meter per second. Now, if today I check the structures of that area which have been constructed recently or maybe 10 years back, they may not really be okay, adequate. So there is something to be discussed, debated, that what should be done and what is the reason. There must have been enough reasons. There is a complete set of data from the meteorological stations, but people, the consultants are finding it really difficult to convince their clients that why the cost suddenly has jumped up. So these are the issues. This is 2016 wind code, NBC. From here, section 4 of chapter 6. So everything is mentioned here if you want to read about the latest revisions. Abhi iske baad revision to nahi hua hai, but certainly there are several issues in IS 875 which are being discussed, and there is a need to revise the code again. And there is a committee, there is a subcommittee of BIS which is working on it. Revision of IS 875 part 3 in corporate. There are a good number of people, including SCRC team, RWDI team, and other teams, IIT teams, meteorological people, that this needs to be changed. This code, I'll share the relevant part. This deals with the buildings from 50 to 250 meters. They say beyond 250 meters, refer something different. Do performance-based design, this, that. It's okay. Lateral drift. When design lateral forces are applied on the building, the maximum inter-story elastic lateral drift ratio under working loads, unfactored wind load combinations with return period of 50 years, very clearly written. Some people misguide this with another clause which is given later. But for lateral drift, it is very clear, unfactored wind load combinations and combinations, not the wind load alone, with return period of 50 years, which is estimated based on realistic section properties. And realistic as in 7.2 means with the We will see stiffness, modifiers and all that. For a single story, the drift limit may be relaxed to height by 400. Whereas for earthquake, it is height by 250. Why? Again, in earthquake, you are permitted to go into non-linear zone. So a higher value of lateral drift is allowed. While in case of wind, it is elastic. So height by 500 is allowed only. Then, yes, here. Loads and load combinations. Wind effects for buildings with height greater than 150 meter or with complexities in plan or elevation geometry or sited on complex topography with group effect or interference effect or whose natural period is greater than 5 seconds means too flexible. Wind effect shall be determined by site specific wind tunnel. Very clear. There is no if and but. If I consider a building of say same 200 meter Loda Bellissimo, 64 floor, this code will say 6.4 seconds period. So it is crossing 5 seconds. So wind tunnel testing should be done. So all such wind tunnel testing should be done with this. And site specific wind tunnel testing, they have mentioned. When wind tunnel studies result in lower story shear and moment, then those calculated based on IS 875 part 3, this is important. The minimum design wind based shear shall be at least 70% of that derived based on IS. मतलब अगर आपका wind tunnel में कम आ जाता है, people say IS code is conservative, estimates higher, so they go for wind tunnel testing. And they say हमारा तो कम आ गया, we are getting lower values. Okay, it's okay, but you can't have less than 70%. The relative distribution of story shear shall be as obtained from wind tunnel studies. The distribution will be same as in wind tunnel, but it should not be less than 70%. When wind tunnel studies indicate torsional motion, because code doesn't give any torsional guidance, structural system of the building should be modified suitably to mitigate the torsional effect, so as to bring the torsional velocity below this in 10 years. Then important is lateral acceleration, this clause. From serviceability considerations under standard wind load with return period of 10 years, the maximum structural peak combined lateral acceleration in the building for along and across wind action at any floor level shall not exceed the values given below in table 4. So this should be checked. You can check it theoretically also with the calculations. Yeah. The rest of the things are common, but as far as wind is concerned, these are the things. And as given in 7.2, these are the realistic modeling is this. Computer modeling shall consider the following. So all these should be flow diaphragm, cracked cross-sectional area properties, means this table 6. This to be used in that lateral drift calculation. Serviceability. It is okay from my side for today, and I'll just stop sharing and then we can talk to the people. Thank you. Thank you so much.
Thank you, sir. So what we get is that in the NBC 2016, the Amendment 1 and Amendment 2 is already there. Am I correct, sir?
Yes, sir.
Okay,
Yes,
sir.
No. NBC doesn't include that everything.
Okay.
But I think yes. Dr. Hari Krishna, can you please unmute him? Yes. NBC 2016, does it incorporate Amendment 1? आपकी आवाज नहीं आ रही. I think he's saying yes, it is. Okay. Definitely.
Okay.
No, not the amendment 2, because it is published after that.
After, in 2020. as
Amendment
you
1,
mentioned.
those typing mistakes. Amendment
Okay,
1.
sir. Okay. So we have certain questions in the chat box. I see 22 questions.
Yes.
So
yes.
you please go through the chat box and try
Okay,
to
I'll open up.
both of them. Both of them.
Both means? Sir.
Dr. Prem Krishna is also there.
Yes, sir. Yes, sir.
Yeah, sure. I'm here.
So please
Dr.
go to the
Gupta
chat
text-
box.
Dr. Gupta, any question you want me to answer, I'll try.
Okay.
Yes, sir. There is a question from Mr. Narayan. Kindly explain the suction process analytically. It is when the pressure, when the wind streams leave any area, it is very simple. Even you can visualize that when you keep a piece of paper on your table and just blow it on the top slowly, then it starts lifting up a piece of paper. Same phenomena when the side of the building, there's a release of the wind stream, then because of the corner, you can say there is a high pressure from the high pressure in the middle to these edges, and then it releases, which goes away from the surface. So when the stream goes away from the surface, it sucks the air from the surface in contact. That is suction. Okay. Amendment number 2, it is there. Does vortex shading occurs only in a crosswind or also for long wind? In a crosswind only. Actually, a crosswind is a consequence of vortex shading. Otherwise, a crosswind cannot generate. Both directions. Yes. So what are the design cases in which we have to consider dynamic wind loads? I think after this question, we have answered that.
Yes.
Natural frequency of first mode can be calculated by software or by empirical formula. Sir, it can be calculated by software provided we are able to model the structure perfectly. Basically, the natural frequency would be a result of 2 parameters only, mass and stiffness. What all masses are contributing to the structure and what all elements are contributing to the stiffness. As far as RCC elements are concerned, their stiffness is perfectly modeled, no issues. But as far as other elements like masonry walls, infill walls, how well we can model, and that is why this empirical expression, there is a research paper, I am not remembering if Dr. Krishna can give that, in Japan or in, I think in Japan, there were about 150 buildings on which the ambient vibration study was done. They were comprising of different categories, different types. And then that graph was plotted, height versus the natural frequency. And then H by 46 was one for the bare frame building like that. And H by 70 for the building with walls and all those came. But I think 0.1 N is a little bit on the higher side as people have reported. But certainly, as on date, very rarely there are tall buildings will not be with the bare frame. Tall buildings, you always have the shear walls or other system. And then 0.09 H over square root D has to be considered, or there's no this one. So 0.09 H over square root D, now that gives you natural period in both the directions equal. If my building plan dimensions are 25 by 50 meter, my shear wall may be oriented in one direction more and in other direction less. But that expression gives same natural period, which is not correct. It should be made more rational with respect. It should be related to the stiffening elements there. I think that is better. How to read the value of CFG from figure 10 and 11 of code page? That is the crosswind response. As I explained you that you have to calculate that non-dimensional parameter, and corresponding to that, from that corresponding building graph, you have to see the value, CFS. What are the varying factors that affect a gust factor formula given the code? Sir, every fact, primarily it is the face width B of the structure, terrain category, turbulence intensity. These are the parameters which affect the gust factor. I did a sensitivity analysis also during my PhD. What are the parameters which affect the long wind response, which affect more, which less, long back, 96. So whether explanatory handbook for this code is ready for users. There is a draft copy only as of now available. Solved examples we did. They were updated up to the 2015 version. But after the second amendment, some more corrections may be needed. That I have not done yet. But as of date, as I told, there's a BIS committee which has been made for revision of IS 875, and same committee will also take up the task of handbook preparation. Though I have volunteered there also, and Indian Association of Structural Engineers, they have also assigned me this task of preparing the handbook. So that is under preparation as of now. Yeah, my question is correctly written and at the drafting stage. Why, sir, code came into very tough to answer. It is termed as 2016, but actually it was published in 2017 March. What is the appropriate scale factor range to do wind tunnel testing? Generally 100 to 400 geometric scale. Depends on the facility, wind tunnel facility also, and the size of the structure. So when the code suggested interference factor for different zone, then why we should consider the linear interpolation of 1/3 height? I could not get this one. Abdullah, I could not get the meaning of this. Please, if you can explain and type again. Can we follow 16700 RCC tall building structure guideline for steel tall building? I think yes, it doesn't specifically say, but all the structural message for the structural system and everything, they're more about the concrete or concrete shear walls or like those kind of system. Purely steel tall building, maybe some provisions may not really fit in. Actually, that is an issue with the country. We have always been pro RCC, but Insdag need to take up that. Even if right from our education days in the college, if we used to ask option between this or the even teaching faculty was not available. Enough teaching faculty for steel is not available. So maybe a capacity building program on the steel design is needed in the country.
Yeah, I was one outsider teaching steel all the time.
Yes, sir. Actually, sir, recently I was discussing a project. It's a huge project. I'll not disclose the name, but there is a requirement of heavy fabrication, and means like 50 mm thick, 80 mm thick, 100 mm thick plates. So the consultant who is from Dubai was worried about whether it can be done in India and how. So then I was called there in that meeting. It seems you have some experience. Please tell us. But we don't have. Maybe we'll have to develop some more thing on that. Could you kindly explain the famous statement of a wind engineering expert? For wind load, always design a building which confuses the wind. Very good. I think, sir, you can be the best to answer this question.
What's the question?
For wind load, always design a building which confuses the wind. Very good statement.
Yeah, that's a good statement. The whole idea is, and in fact, if you see some of the latest designs in tall buildings, you find all kinds of shapes and twisted buildings and, different geometries. And the result is that you actually end up confusing the wind. Why does a crosswind oscillation pick up and become dangerous? Because you have the shedding of eddies. If at a regular interval the eddies are shed, you get a regular force which is oscillating the building. But if you confuse the building, so to say, and this regularity is broken, then this phenomena of vortex shedding oscillations will get curtailed. I think the statement that has been made is for that reason. Okay.
Primarily doing aerodynamic modifications so that the wind effects, the dangerous wind effects are reduced. That is the confusion.
For example, if you cut the corners of a rectangular building, then the crosswind oscillations die down. If there is an issue of crosswind oscillations for a particular building which is rectangular, and if you cut the corners, then the crosswind oscillations die down to an almost insignificant level. So that's one way of confusing the wind, if you like.
Yes, sir, correct.
Are the questions done?
Yes. Composite columns, what will be cracked value? This doesn't cover the composite column. That's what I'm saying. See, all the modifiers and everything we are talking is about the RCC. Steel or steel concrete composite is not covered here. And it will not be valid for those. Keshavan Periyaswamy. I'm Keshavan, research scholar, INIT Puducherry. Now I'm working on the behavior of slender structures under the action of wind. Here we have a slender structure which is having a height of 37 meters and a width of 2.3 meters. It was constructed on 14 upon construction. People felt vibration at the top. Okay, means people can go on the top. Now we check the accelerometer and the peak acceleration value exceeds the permissible value, which is prescribed by 16700 under this. But actually, a 2.3 meter structure, what is that? Is it a habitable building? Whether IS 16700 is applicable to this? Actually, the serviceability criteria will be different for this structure. It will not be the same as applied for a building where people are going to live. Those acceleration limits given in 16700 is from the human comfort criteria. Those who live there whole day. But on it, I think this must be a tower where people must be going for 10 minute, 15 minute kind of thing. And feeling is okay. But if you are not exposed for a longer time, then there is no problem. It is like that. So you need to be more, think in that term. See, every code, serviceability criteria has to be defined for every structure separately. I was working on a flag post, India's tallest flag post. It was proposed to be 105 meters tall. And that flag itself was more than the size of 2 tennis courts on the top. So by anything, that sway at the top was not coming less than meters. And it's okay. If the flag, as long as structural, there is no issue with that sway. If the flag is waving by 1 meter or 2 meters, it's okay. Its functionality is not affected. That's the thing. What code we should use for steel tall structures? See, as of date, India में तो केवल एक ही code है, IS 800, and nothing else. We are in the process of a draft code, ductile detailing of steel structures, which has come for the wide circulation. If you have received it, I request all of you to please go through it, and if there are any comments, please share with BIS. Refer 8.3 clause, just a moment. 8.3 of IS 875.
Oh, that's Mr. Abdullah's question, right?
Yes. 8.3 of, I'll just open 8.3. Tall buildings based on studies, the interference factor which need to be considered corresponding to this. Actually, interference factor, you can have the interpolation because these zones which have been framed are made out of the you can say, experimental result. The contours have been plotted and then these zones have been identified. So interpolation on a intermediate position for the factor is perfectly okay. The entire analysis is approximate as of now. Whatever has been given in the code is only a preliminary guidance, just to understand that these zones will have the enhancement. But again, there's a critical structure, more important, go to winter. At least it gives some idea. That's all. That's all.
Let me just come on to this one.
Sir.
Abhay. You know, this code that came out in 2015-16, the first draft was made in 2002 or 2003, I think. And it was the first draft which at all thought of interference being included. At that time, no code in the world had talked about interference effects. But obviously, it had to be something which gave you just approximate values. Now, 20 years down the line, I'm sure there is much more information available. And also, I was told some of the other codes are now including the effect of interference in some way. The Australian code, I think, is doing that. So I think the Dr. Hari Krishna committee, subcommittee, which is looking at the revision of IS 875 Part 3, this is one of the issues which they may perhaps take into account, and using additional data, try to improve this clause on interference. Similarly, when this factor for cyclone K4 was introduced, it was through the Indian standard 15498, which is to do with cyclone affected structures. And this was again something which came about 20 years ago. Since then, and according to that stipulation, the cyclone affected zone is 60 kilometer wide on the east coast and 60 kilometer wide on the Gujarat coast. Now, in the last few years, there has been increased cyclonic activity on the west coast. And I think this is another issue to be reconsidered, whether both the coasts should be likewise treated as far as K4 is concerned. The third point, I think, is that, as I said in my presentation, V is a very crucial issue. And when you multiply V with a factor like K4 or whatever factor, it increases that value of V. And there is a need to keep on revisiting our study of V, or the basic wind speed. There is a study right now going on at IIT BHU, sponsored by the Bureau of Indian Standard. And they are looking at the cyclonic wind speeds. Maybe they, in due time, come up with the revised factor, K4. So those are 2 or 3 points I thought I'd share with you.
Good, sir. Dr. Ajay Shah saying good presentation. Shah Sahab, namaskar. I hope you are doing good. What will be the design consideration or guidelines for building in coastal region? So already, sir has already answered that. Prone to high velocity, we must refer to IS 15498.
15498
and 15499. 498 is more relevant. So please refer to that, and it elaborates the thing more.
Of course, K4 has now come into the NBC also.
Yes, K4 is coming. For interference question 875 to, I think Abdullah, I have answered your question. Sure, presentation I'll share with everybody. Thank you. All the questions on the chat box are over.
Yes, sir. You have finished all the questions in the chat box. Just for the participants, the total presentation will be uploaded in your YouTube channel might be a day will be required. So you will be getting that. And we thank both the presenters, and it was a mesmerizing program where still we have some doubts which might be cleared after we go through the codes. So thank you very much, and also thank you all the participants. We'll be coming up with another set of our this sort of a lecture. Please do follow in our website. We will upload our next programs time and again. So this is a series which we will be continuing, might be on various topics. We will also share you the feedback form. You can give your advices on which sort of a topic you will be interested to get from our side. So with this, I thank everybody and end this today's program. Thank you, sir.
Thank you very much.
Everybody. Thank you, sir.
Thank you, Mr. Ghosh.
Yes.
Thank you.
I think I did, yes, I did complete. I left some slides in the end, but time was not there.
Oh, okay.
Thank you.
Okay, sir. Next time, it's always there.
Okay, thanks very much.
Thank you, sir.
Thank you.